How do residual stresses affect materials? Imagine a metal part that looks perfectly smooth and solid, but inside, it's holding hidden forces. These forces are called residual stresses, and they stay locked inside even after all external forces are gone. They happen during manufacturing processes like welding, cooling, or shaping. When metal cools unevenly, some parts contract more than others, creating internal stresses. Welding can also cause residual stresses because of rapid heating and cooling in specific areas. Residual stresses can be either tensile, which pull the material apart, or compressive, which push parts of the material together. These internal forces change how the material behaves when it is used in real life. For example, if a component has high tensile residual stress on its surface, it becomes more likely to crack or break under load. On the other hand, compressive residual stresses can actually help prevent cracks from forming or growing. When a material is under cyclic loading, like in a machine part that moves repeatedly, residual stresses play a big role. Compressive stresses at the surface can slow down crack growth, making the part last longer. But if tensile residual stresses are present, cracks can open more easily and spread faster. This can lead to early failure and costly repairs. Residual stresses also influence how materials react to corrosion. Tensile residual stresses make materials more vulnerable to stress corrosion cracking, where cracks grow due to the combined effect of stress and a corrosive environment. Conversely, compressive residual stresses can help resist these failures by reducing the stress at the surface. Another way residual stresses affect materials is through distortion. When parts are heated or cooled, they can warp or change shape. This distortion can cause misalignment in assemblies, leading to mechanical failure or malfunction. For example, a turbine blade with uneven residual stresses might warp over time, affecting its performance. Residual stresses exist at different scales. Large-scale stresses, called macro stresses, can cause visible cracks or warping. Micro stresses are within individual grains of the material and influence local strength. At the smallest scale, nanoscale stresses affect atomic bonds and overall material properties. These stresses come from various causes. Plastic deformation, where a material is bent or stretched beyond its elastic limit, leaves internal stresses. Uneven cooling during heat treatment or welding creates thermal gradients that generate internal tension and compression. Changes in crystal structure during phase transformations also produce residual stresses. Engineers sometimes intentionally introduce beneficial residual stresses. Processes like shot peening or laser peening create compressive stresses on the surface, improving fatigue life. But it is equally important to identify and control harmful tensile residual stresses to prevent unexpected failures. Techniques like X-ray diffraction or strain gauges help measure these internal forces, giving a clearer picture of the material's health. In the end, residual stresses are like hidden forces that can either protect or weaken a material. They influence how long a part lasts, how cracks grow, and how well it resists corrosion. Managing these internal forces is key to making reliable products and avoiding sudden breakdowns in the mechanical world around us.